Okay, let's move on to our next speaker. D.Hendrix is going to talk to us about chemical reactivity and potential toxicity of lunar soils.
I think it's this one. So unfortunately, my camera is not working at the moment, so I will have it turned off.
Okay, no worries.
Okay, so thank you. So we go on just to the next slide. So the purpose of my work is to understand the health effects of lunar dust. And the way I do that is I look at the reactivity or how much OH radicals generated by terrestrial minerals and lunar stimulants. And the reason I specifically look at OH radical is because OH radical is theorized to be cancerous to lung tissues. So I'm part of the RISE-2 team, and within that team, I'm part of the Theme 3 group. So what the group does is we probe the health effects of lunar dust. And so what we more specifically do is we try and develop the next generation of better lunar stimulants. I myself try to assess the reactivity of these stimulants, which we're going to talk about today. And there's others in our group who look at the toxicity of these stimulants in cells and living animals. So far what we've done is we've obtained and characterized terrestrial minerals similar to what's found on the lunar surface. We've also obtained lunar stimulants and we've tried to reduce them to sort of replicate some of the space weathering effects. And so far we've done this with JSC1A, LMS1, and LHS1. With all these materials, what we've done is we've measured the OH radical generated or the reactivity of these materials using a technique known as electron paramagnetic resonance spectroscopy or EPR spectroscopy. So with EPR, we're able to measure the amount of radical in solids, liquids, and gases. In our case, we're measuring it in liquids. So first we started using JSC1A because that's kind of what we had readily available. So JSC1A was originally meant to be a lunar Mare stimulant, and it was developed to primarily aid in engineering projects related to lunar exploration. So some physical properties like grain size and specific gravity are pretty much on point with what you observe in the lunar dust. There are, however, a lot of downsides to using a JSC1A. There is only a trace amount of pyroxene, and if you're trying to replicate the lunar mare, that's no-go. The amount of plage present in JSC1A is too high to be an adequate mare stimulant. The plage chemistry in JSC1A is between about AN64 and AN70. On the moon, you have about AN85 plus for most of the time. The olivine in JSC1A is too phosphoric, or there's too much magnesium present in the olivine. There are clay minerals present in JSC1A, and there's no clay minerals present on the moon. The JSC1A has too much titanium magnetite compared to ilmenite, but the primary drawbacks are that there's no agglutinated glass nor metallic iron, which are primary characteristics of lunar dust. So we decided to get better lunar stimulants. So we got the Lunar Mare Stimulant 1, or LMS1, and we got the Lunar Highland Stimulant 1, or LHS1. So we have LHS1 here at the top, that I'm circling. And here at the bottom, we have LMS1. So the main advantage of these two stimulants are that the mineral proportions, or the percent like olivine, plage, and pyroxene, are very close to what you find in the lunar mare and the lunar highlands. However, there's still drawbacks in using the stimulants in that they're deficient in iron and calcium, and there's too much magnesium, sodium, and potassium. And it kind of just highlights the disadvantage of having to rely on terrestrial materials in making lunar analogs. But again, the primary drawback are that there's no agglutinated glass nor metallic iron. So we can get around the metallic iron problem. And so what we did was we added some lunar stimulant to the center of this glass tube. So I'm kind of circling right here in the middle where we put our samples. And this glass tube is being flushed with hydrogen. And when that's happening, we were able to put this glass tube into this furnace back here, and we heated up the sample 900 to 900 C for 15 minutes. And when we removed our sample, we noticed that the sample was darker. So that's how we know how we did, in fact, create some metallic iron on the surface. And here we have further proof that we created metallic iron. So this is an SEM image of a bunch of JSC1A grains. And you may notice that there's a bunch of little blebs all over the surface. So I'm kind of just going around pointing to some of the blebs on the surface. And these blue arrows are pointing to some random blebs just to make it a bit easier for people to see. And so that's in fact metallic iron. There was a study done like 25 years ago where they took Apollo samples and they ran it through a really similar reduction method that we used, and they were able to determine that all the little blebs that formed on the surfaces of their materials were in fact metallic iron. And so to measure the OH radical generated by these samples, what we did was we took about 200 milligrams of sample and we incubated it in a solution of DMPO. So this molecule right here is DMPO. And DMPO is able to trap radicals such as OH radical, which is made by the sample. And this then reacts to form this stable compound here on the left. And the EPR can then measure this compound because this compound has a very high half-life. So we have plenty of time to make our measurements. We can't measure OH radical directly because OH radical is extremely reactive by itself. So here we have some data that we obtained from our EPR. And so here for the graph on the left side, we have just various terrestrial minerals, and we plotted their reactivity on the y-axis from 0 to 1.4. And on the x-axis, we plotted their iron oxide weight % content. And so here on the bottom left of the graph, we have minerals such as albite, bitonite, labradorite, and quartz. These are felsic minerals. These are minerals that are not rich in iron. And they're pretty much not that reactive. We use quartz as a control. There's not really much quartz found on the moon at all, but we use it as a control because it's known that it's not that reactive, and it came out around 0.1, which is around where we expected it to come out. Our mafic minerals, or our more iron-rich minerals like diopside, olivine, and augite, were much more reactive. Olivine and augite generated about 1 micromole of OH radical. So pretty much the main takeaway of this side is that the more iron oxide you have in a mineral sample, the more reactive it is. And here on the right side of the slide, we have our various lunar simulants. We have JSC1A right here on the left side of the graph. So non-reduced JSC1A makes only about 2 micromoles of OH radical, or a little bit less. But once we reduce it here, it makes almost 4. So it's a significant increase in reactivity upon adding metallic iron to the surface of our lunar simulant. Now let's move over to the Mare simulant. The non-reduced Mare simulant makes a little bit more than the non-reduced JSC1. It makes about 2, but if you look at the reduced Mare simulant, it makes more, but not that much more. This is kind of odd because the lunar Mare simulant has a lot of mafic or iron-rich minerals present. So I expected this data or this bar to be a lot higher, and it's not. So it's a bit odd. Now I want to try and go back and look at that again and see if we get those same results. For our Highland stimulant, the non-reduced one makes a little bit more than 1, so it's kind of as expected. There's not many iron-rich minerals present in the Highland stimulant, so it came out about where we expected it to. But then if you look at the reduced stimulant, the reduced Highland stimulant, it makes almost 3, so it's a significant increase in reactivity. And the main takeaway from this is that the addition of metallic iron causes a very large increase in reactivity. Because if you look at the numbers like 4, 2.5, close to 3, that is well above what you see on this side, where we're going from 0 to 1.4. So it seems that not only does iron oxide affect reactivity, but metallic iron does as well. And metallic iron seems to affect reactivity even more than just iron oxide content by itself. So this has a lot of implications for lunar dust reactivity, since lunar dust itself is known to have a lot of metallic iron. And so we talked about the lunar simulants, their reactivity, the terrestrial minerals and their reactivity, and how the more iron-rich materials are more reactive, how materials that have metal iron in them are even more reactive. But there are, of course, drawbacks in using these materials, and the fact that they're made of terrestrial minerals. So you're lacking the high amounts of iron and calcium you observe on the lunar surface, and you have too much magnesium, sodium, and potassium. So one way we can sort of get around this is we can make our own samples. And Hannah kind of touched on this a little bit in the previous talk. So here I have the, thanks. So here I have the olivine solid solution series. So we made a few different types of olivine in the lab in the past few months before all this started. So here, down here on the x-axis, we have here magnesium, Mg2SiO4 or 4 straight, and at the end we have phthalate or Fe2SiO4. And interestingly enough, the end numbers are really not that reactive, but once you start moving towards the middle, the reactivity actually keeps on rising until you get to this peak right here, right at the 50-50 mark. So this is a really interesting result. We had no idea what was going to happen when we ran this. We actually thought that the phthalate, the Fe2SiO4, would be the most reactive because, as I said in the previous few slides, that the more iron oxide you have in a silicate mineral, the more reactive it is. But for some reason, it is our least reactive mineral, pretty similar to that of the forsterite, which has virtually no FeO in it. But this is a very interesting result. So the good thing about this is that we can see what the reactivity looks like across the olivine solid solution series, but we don't know why the reactivity shows up the way it does. So that's something that we have to look at in the future. It's going to be a really big challenge for us. And I also plotted the olivine from the previous slide. This is actually San Carlos olivine. This is FO91, so it plots around here. And it's not super far from this trend line. So it's very likely that that the left side of this graph is probably going to look a little bit like it does here on the right side. And so to conclude, metallic iron on the surface of our lunar stimulants caused a significant increase in reactivity. So it seems that metallic iron causes a much larger increase in reactivity compared to just iron oxide by itself. The lunar Mare stimulant, which has more mafic materials, generated about twice as much OH radical as the Highland stimulant, which doesn't have that much mafic material in it. And when we look at the individual minerals themselves, iron-rich minerals generate much more OH radical or much more reactive compared to felsic minerals. And so by looking at reactivity on a mineral by mineral basis, like we did with olivine, like looking at just a solution series, is that we can see how reactivity changes across a mineral solid, a solution series, and we can actually make what's on the moon. We don't have to rely on these very hard to get lunar dust samples. We can just make whatever we want in the lab, although it's not in very large quantities to be like a stimulant that we can sell in kilograms. It's very, we can make enough for our work. And so that's one advantage of that. We can just make what's on the moon, and we don't have to worry so much about impurities, because with terrestrial minerals, you might have some like clay minerals present in your minerals. And so we don't want that because there's no clay minerals on the moon, and that might alter the results a little bit. And so I'd like to thank all these people here, and I'll take any questions you may have.
Thank you, Donald. We have one question in the participant. Micah Shabel has raised his hand. Micah, you can go ahead.
Hey, Donald. Great talk. That was very interesting. So I had sort of two questions. The first was, I didn't see where, maybe you mentioned it, but I didn't see you mention the FeO content of the stimulants. And secondly, did you do anything to those stimulants before you tested for the unreduced ones? Did you do anything to just the powders before you tested their reactivity?
So for these powders, what I do for all of them is I hand grind them for like about I hand grind them for like about 10 minutes by hand before I test their reactivity. And so by doing that, we're sort of trying to stimulate space weathering to some extent. So space weathering is known to break bonds in lunar dust. And so by mechanically altering our samples, we're actually making them more reactive. We're breaking bonds on the surfaces, and thus we're seeing higher reactivity. So I pretty much just grind them. But when I test the reactivity of both the reduced and the non-reduced, I do the same thing. I just grind them by hand for 10 minutes, and then I test their reactivity.
So the other part was, did you measure the FeO content of the stimulants?
So we do have the FeO contents of them. So for the Highland stimulant, it's around 3. And for the Mare stimulant, it's around 8. So let me go back to that. You want me to go back to that slide? I can go back.
Yeah, that's exactly what I was hoping for. Yeah, right there.
Yeah, so I didn't plot them on this because this is data I had from like an old publication. This is the one on that I'm circling now is more recent data. But yeah, the Lunar Mare stimulant has significantly more FeO content versus the Highland stimulant itself.
Gotcha. Thank you.
Yes, of course.
Okay, thank you again, Donald. I think we should move on to the next talk.